Thank you everyone for joining us for this webinar 2 of Slide2 webinars series. Today's webinar is on seepage and slope stability analysis. And I will be presenting this webinar. I'm Ali Reza, one of the geomechanical specialists at Rocscience. And let's just jump right into it. Schematically showing here, you can see that all the outflow and inflows affecting the groundwater regime. So you can have precipitation, then you have flow of this precipitation water on the ground surface. You have a river flowing here. You're pumping water in and out. And also you have different aquifers here. If you have aquifers in the bedrock, you can see that this is the pore water in the bedrock between the joints and features of the rock mass. And you have pore water in the sand layers. Looking at all these scenarios, we can all simulate them in our programs. There are formulations, there are methods for that. And the effect of this pore water pressure can be included in slope stability calculations in slide 2. Just a brief introduction what we are dealing with here. We are looking at water pressure. If you are looking at this point here at the bottom of these triangles, you are looking at here, your pore water pressure is going to be the height of the water standing on top of that point, if this is the water table, multiplied by unit weight of the water. Now, the concept of effective stress, we have it here. The effective stress is going to be total stress minus pore water pressure. And the importance of this sigma effective is that it is appearing in most of the formulation that we have in calculations of shear stress. So in a case that your pore water pressure increasing, your effective stress is going to be reduced. And in a sense, you're losing your shear strength and you will end up with lower factors of safety in your problems. In slide 2, we have different methods that we can incorporate the pore water pressure in our calculations, in the calculations of factor of safety and stability. Of all these methods, I've listed here the water surface, piezometric grid data, pore water pressure ratio RU method, and we have the built-in finite element engine to do seepage analysis. I have examples for you here on water surface, piezometric grid data, and finite element seepage analysis. The first one, we are dealing with water surface. I have two examples for you. One is an open pit with a piezometric line inside the domain, and the other one is a levee under flood, and the level of the flood, as you see here, is rather high. So just before going to the examples, if this light blue line is your phreatic surface, are going to be perpendicular to the phreatic surface. So if you are calculating the pore pressure at this point, you are not just measuring the depth of this point from the water table, the phreatic surface. You have to calculate this distance, which is HU equal to H cosine squared theta. Pressure is going to be unit weight of water, the depth multiplied by a factor, and this HU factor is depending on this geometry of this model here. In the slide, when we are defining this, we have two options for HU. HU can be custom value or auto. Auto is automatically calculated based on these equations here, but custom, you can assign any desired value that you would like. So HU equal to 1 would indicate hydrostatic condition. And if you have values between 0 and 1, you are actually simulating the hydraulic loss due to seepage. Having HU equal to 1, you're actually overestimating the pore water pressure. So in a sense, you are actually being conservative. So in most example that I'm using here, I'm going to use HU equal to 1. Okay, let's start with the first one. I'm receiving messages that people cannot hear me. I'm just double checking. Can you guys hear me? Okay, I see lots of messages. People can hear me. I'll continue with the presentation then. Just to remind you, my colleagues on the other side are actually looking at your comments and questions here. If you have any questions, please type them in. Some of them will be answered during the presentation. Some of them I will answer at the end of the presentation. Okay, so let's go back to the example. This is an open pit and a phreatic surface. let me start the example here. I have 6 example for you here. The first one, we are looking at this open pit. And as you see here, I have listed all these material properties for you here as well. There are cohesive frictional material. And the groundwater method that we have here is using actually water surface, but we don't have any water surface here. So there is no pore water pressure in the domain here. Let's run this simulation, see what is the factor of safety for this example. Just to make sure we cover all the project setting here. I'm only running for Spencer method here so that we are going to be fast. We can calculate and get the results faster. And also for this example only, I'm using the default option, circular auto refine. In the rest of the example that I present to you, I will be using non-circular and cuckoo search, which is more advanced search algorithm. So let's look at the results here. So factor of safety, Spencer is 1.58. So if your design factor, the design factor is 1.5, this slope is safe. Now let's go back to the modeler. I will copy and add a scenario here. And in the second scenario, I'm actually going to rename it. I'm gonna name it phreatic surface. So in the second one, again, we are using that water surface method. And I will bring in the water surface as a DXF file. So if you're looking at it, I'm going to go File, Import DXF. I select that. Then the window is opening for me. I can go select the DXF file. This is my DXF file appearing here. As you see here, the file that you are looking at, this is only a line here, and I'm assigning water table role to it. I will bring it into the model. And since I want the water table to be assigned to all the materials, I will select all the materials here, and all of them will get this water table as the definition as to define the pore water pressure in the field. Okay. Now you can see in the modeler that I have in the property table here, we have water surface defined here, and HU is using the value of custom value equal to 1. So we are actually a little bit overestimating the pore water pressure, but let's see the results here. So let's run the engine, the slope stability engine. The first scenario, we already have the results for it. We don't need to run it. The second one is the new one. We're going to run it for that. And as you see here, the factor of safety, for the case that we have the pore water pressure generated for it, it's actually 1.22. If I tile the view between these two models, like zoom, you can see that due to the presence of this phreatic surface, existence of pore water pressure below this, underneath this slip surface. Let me activate that one as well. Show values along the surface, pore water pressure. You can see that there is pore water pressure acting beneath this slip surface, and that's why you're getting the factor of safety is 1.2. If the design factor for this slope was 1.5, with the presence of pore water pressure and this water surface, this slope is not safe anymore. Okay. Simply, this example showed you that, okay, pore water pressure just coming to the model is not going to be safe anymore. The second example, we are looking at the levee and a water surface. This is actually an interesting model. What we have here, we will look at the effect of ponded water load and tension crack on the factor of safety. The levee is under flood. The level of the flood on the upstream side is 9 foot, and the whole height of it is close to 14 foot total. Now, this levee, specific levee, has been studied extensively. You can see the specification of this model at the top here, and this has been independent. There's lots of publication, report, and journal papers on this. The failure mechanism that finally people decided that what happened to this levee was listed on the left side here. So this is the failure mechanism. We have the rising water in the channel pushing laterally against the flood wall, and eventually and progressively opening a gap between the flood wall and the outboard section of the levee embankment. In the second stage, you have water entering this gap and increasing the lateral push against the sheet pile. And after that, you have the shear failure. So this is the failure mechanism that is happening here. And if you look at the literature again, for the failure mechanism that we are dealing with water-filled gap, the suggestion is to consider a scenario, something like this here, that we are modeling the water-filled gap by removing soil on the loaded side of the gap and applying hydrostatic water pressure to the wall. So within the scenario that you're analyzing for this kind of simulation, this is one of the cases that you should consider. Now, let me go to the model here and show you how we can do this. Another point that I would like to make here, in this levee, all the materials, you can see the properties of the material that are actually at the top. They are all cohesive material only, so no friction angle. That means that the pore water pressure itself has no effect on the shear strength of the material. And as you will see here, if this is actually polyline in the domain, this is the level of the flood that will be on the upstream. I'm just going to right click on it, convert it to a water table. And just to prove that, okay, the pore water pressure is not an issue here, I'm not actually applying the pore water pressure to the materials here. So I'm just bringing the water surface here. And we are looking at the effect of ponded water load and the pressure of the water, the weight of the water itself, not pore water pressure. Now, the scenario that we are looking at here is no gap. The next scenario, I will open the gap, and we can see the effect of opening of the gap. So let me run this scenario. As you see here, the factor of safety is rather high. Let's look at the results. It's optimizing the slip surface. Okay. For the scenario that we don't have the gap, the factor of safety is 1.5. Usually these are designed for 1.5, so this is considered safe. Now, let's go back to the modeler. And in the next scenario, I will add a scenario here. And in this one, I'll rename it, and I added a gap here. So to generate the gap here, simply, I'm just going to zoom in here so that we can see what I'm doing. I will use our tension crack boundary condition at tension crack. And I will draw the area of tension crack right behind the sheet pile that it is on the side of the flood. So I'll select that one, select the top of the sheet pile, the bottom point, going horizontally, and I'm just drawing a square around the sheet pile. So now these vertical gray line that you can see here, these are the tension cracks. So I actually have a gap, the tension crack open here. The other thing is that I have to fill it with water. So if you right click on these, tension crack properties, and I will go and change the water level to use the water table to assign the properties of the water to these tension cracks. Okay. Now you can see that all these tension cracks have turned blue to the depths of the water. As you can see, it's all over the place. So everything is filled with water now. Now let's save this one and compute. The first scenario is already, we have the results. The second one we are running. You can see the factor of safety actually changing here. Now it's below 1. It is being optimized. And at the end of it, let's look at the results. You can see that when you have the gap and the gap is filled with water, your factor of safety is actually 0.8, well below 1. And that's how this levee failed. If you look at the vertical slices for this problem, and the very first slice, you can see that there is actually a force, a lateral force behind this slice. And if you look at the value for it, So this is actually equivalent to the this value that we have here. This is equivalent to the pressure that you get from the water behind the wall. Gap opening, the water entering the gap, and you have this hydrostatic pressure from the water applied to the mass, the body of the mass of the body that is fading and moving. Okay, so comparing this example with the other one, with the first one we actually looked at pore water pressure in the domain. This second one, we actually only looked at the water load, not the pore water pressure. So there are different ways that water can come into your model and affect your factor of safety. Now, let's continue with the finite element seepage analysis. I have 3 examples here for you, a levee, an embankment, and an open pit mine. Just a brief introduction, what we have in a slide. We have steady state and transient flow. The engine can handle both of them. In a steady state, we are assuming that there is infinite time available for the pore water pressure to equilibrate to applied hydraulic stresses. The groundwater inflow and outflow, they're going to be the same in the domain. And these should be confirmed by the site monitoring data. Examples of this could be long-term post-closure condition in pit slopes, cases that you have highly permeable material where equilibrium of pore water pressure occurs really quickly, or situation where changes in pore pressure are extremely slow so that yes, you can assume that there is no transient effect. On the other hand, we have the transient flow. For transient flow, you are looking at the response of the system to the changing of hydraulic stresses. Examples of this could be excavation of a pit, lowering of water level due to mine dewatering, impoundment or dewatering in dams, flooding, rainfall, or any other phenomena that is actually time dependent and not permanent. Just a brief introductional definition that we will be using in this example. If you have a point A in the domain at this depth from the surface, and this is below water table from this point, and you are measuring all the Z coordinate from a datum, your total head would be H, which is the distance from the water level to the origin that you are measuring a vertical displacement. Your pressure head is going to be psi, which is the height of the water standing on point A, and your pore pressure is going to be psi multiplied by gamma W. Now, I describe these because when we are going for numerical modeling, finite element simulation, we are dealing with boundary value problem, initial boundary value problem in some cases. You need to define boundary conditions. It is finite element method. So these are the boundary conditions that we have for seepage analysis. Total head, pore pressure, nodal flow, which is pumping water in and out of the system. We have infiltration, seepage face, and for the transient analysis, we have all of these boundary conditions that I mentioned above, but we can define them in a time-dependent tabular format. A couple of boundary conditions that I will be using in this example is constant head. So looking at this schematic diagram of embankment, you can see that in ABC and EFG, these 2 areas, we have constant head. And this constant head is actually attributed to the body of water standing on upstream and downstream of this embankment. Now, when we are talking about constant head at the location, that implies that you have inexhaustible supply of water there. So looking at the left picture here, if you have a swampy area or a river flowing here, you can assign the constant head in this area. If you are excavating a pit next to it, we are looking at the middle picture, and the river still flows or the swampy area still stays there, still you can get that total head constant at this area. There is no problem with that. But in case you are dewatering water so much that the swampy area will dry, the river will disappear, that means that you don't have that total head constant here anymore. Now, the other boundary condition that I will be using in these examples is the seepage face. Seepage face simply means that total head must never exceed the elevation head. So if you are looking at H and elevation head Z, that means that H is less than or equal to Z. That means that your pressure head psi is less than or equal to 0. And that means that your maximum pore pressure is limited to 0, or there is no water standing on top of this node. So if there's any water buildup above this point, that water will flow away or evaporate. So there is no water on top of this point A. Physical meaning of this is a saturated zone intersecting ground surface at atmospheric pressure, and water discharges from that point as evaporation or downhill film of flow. As you can see here, you have this trench here filled with water to this elevation, and you have this aquifer next to it. And these two areas are where we have the seepage face. So water freely flows from the side of this trench and goes into joins the level of the water that we have in the trench. The general location of these boundary is known to us, but the length of it is not known prior to the calculations. When we solve the simulations, we finish the analysis, we know the length of it. Now, let's do some examples here. The first one is a levee and relief wells. What we are looking at here is a levee here, the yellow material, and we have a sheet, we have a retaining wall as well. And the water level in upstream is standing at the elevation 115 feet, and downstream you have the seepage face, and the elevation is 106.5. We are looking at the effect of having the relief wells, or we don't have them. What is the effect of it on the flow of the water, and what is the effect of that on factor of safety? Okay, example number 3. Start. So to start with, this is the example. You see the geometry. What I would like to do, I would like to do finite element analysis for seepage analysis. You have to go to project setting, groundwater, and change the method to steady state finite element. Okay, we are not doing any advanced option here, so that's good. Clicking OK, then you will have a secondary tab here. We have a slope stability tab and a steady state groundwater tab. So in the steady state groundwater tab, you define your seepage analysis, the finite element seepage analysis, and in the slope stability, you can run your slope stability analysis. When we are doing finite element seepage analysis, we need the mesh. In RS2 slide, all the programs that we have the one-click mesh button. If I click this, the mesh is generated for us. So this is the default mesh. Since I have more interest in the area that levee exists there, I am going to refine the mesh in that area. So I'm going to go to mesh setup, depth drop-down menu, increase the density, a window. I'm just going to draw a window around the area that I would like, which is around the levee. And we now have a finer mesh in that area. So if you have finer mesh in that area, means that you have more nodes there, you are doing more calculations there, you are evaluating the pore water pressure more accurately in that area. Now, if I run this engine, you can see this is compute groundwater only. If you would like to do the groundwater analysis and also seepage and also slope stability analysis, you can go to the slope stability tab and use this other calculator. Pressing this, it will run the groundwater engine first. The blue one will appear now shortly. And after that, the slope stability will appear. I forgot to assign the boundary condition. Okay, let's go back to the model. So we had in upstream, we had the total head of 115. After mesh, we are going to boundary condition. The total head in upstream is 115 feet. And we are assigning this boundary to the boundary sections. So behind the wall, this area, and you can actually drag a window around the area that you would like. So upstream is going to get total head of 115. And you can actually see that water is schematically shown here. This is where the water stands for this example. Okay, now run the analysis. That was the groundwater engine, the blue one, appeared and disappeared. It's a quite fast engine. And the factor of safety that I'm getting for this scenario is 1.19, which is usually these are designed for a factor of safety of 1.5. This is not good enough. Now let's go back to the modeler. I'm going to copy this scenario, add a scenario here. And in the second one, I will put the relief wells in. So the way that I'm assigning these relief wells, the relief wells, the way they work, they will, this is the area that I'm actually going to assign those relief wells. They will set the total head along the relief wells to be the same as what you have at the top. So if the elevation is 106.49 at the top, this area is going to get total head of 106.49. I can get the boundary condition from there and assign it here, or I can just right click here and say the total head here at the bottom corner here, 106 or 0.49. So in this case, now I have relief wells assigned in the domain. I'm hoping that installing these relief wells can increase my factor of safety and bring it to an acceptable value. Okay, the second scenario with relief wells, this is saved, and we are calculating this one. Okay, now I'm actually using my own laptop here, but yet again, you can see that the calculations are pretty fast. I can actually run the whole groundwater engine, slope stability engine all together and present the results live for you. Now, let's tile the view, like zoom and look at both simulations here. The one that has the relief wells, I'm actually changing the contour to total head so that we can see the difference much better, is giving us factor of safety 1.6. The other one is giving 1.2. And if you look at the location of the water surface, the piezometric line, you can see that in this one is actually the one that has the relief wells is much lower. And if you activate the pore water pressure along the slip surface in both of these, actually I closed the model. Let me open it again. You have much lower values in the case that you have that pressure head, those relief wells installed here. Yeah. So you saw actually the changes that you have for the changes that this relief well is going to affect. They do in the groundwater regime here, and your factor of safety increases by significantly. And this one, if your design factor is 1.5, you are safe. Okay. Let's continue with the presentation. I'm just going to close all these files. This second example using finite element would be designing a drainage system for this open pit mine. We have water table standing on the left side of this opening in this open pit, and we have dry area in the pit area so that we can make it workable area. The way this one works, in the original configuration, when we don't have the drainage system, let's look at the groundwater analysis, you have an aquifer here or a reservoir here that is providing you this constant head on the left side. Now, on the right side, since you're having it a dried open pit so that you can make it workable area, I have assigned this seepage face here so that you can see if the water comes in, it will be extracted and it's going to be a workable area for the people that are working there. Looking at the results here, you can see that in this case, the factor of safety is actually below 1. And let me just deactivate the boundary conditions here. You can see that the water surface, this magenta line, is actually touching the faces of the excavation. Now, what I'm going to do in the second scenario for this example, I will install drainage system along these boundaries, horizontal drainage system. Let me just copy this, rename it with drainage. And the way these drains work actually is going to be, okay, if the water comes to these drains, the water will be taken out. In other words, I'm actually saying seepage face. So I'm just going to assign seepage face to these boundary conditions. And by doing that, I will be dewatering the face of the excavation, and we will have higher factor of safety, hopefully. So comparing these two scenarios, this one has those drainage, this other one does not have them. Let's calculate all these factor of safety and seepage analysis. The first one, we have the results for it. The second one, we will be running the analysis for. Now, this example is rather complicated. All the material properties and stuff that we have there, they are using nonlinear hydraulic conductivities, especially for the unsaturated case. We have so many options for that, like Fredland zinc formulation. We have simple function that we have developed here, Bang-Newton, all these functions that are used in the literature to define the hydraulic properties. We have them in the slide included. That's the groundwater engine. It's still running. It's going to take a couple of seconds more than this. And when this is done, the slope stability engine will jump up and run the slope stability analysis, and we have the factor of safety. Okay, now let's take a look at the results here. I'm just gonna tile the view so that we can see them side by side. I'm just gonna change this one to total head as well so that the contours are similar. You can see that by installing these drainage systems, the water surface has been pushed back and you have a higher factor of safety. If the design high factor of safety for this stove was 1.2, for example, with these two drainage systems, you have obtained that goal and you're okay. Okay, let me close these files, go back to the presentation. The last example that we will do finite element here is a transient drawdown. What we are looking at here, we have this embankment here. Initially, the water table stands at coordinate elevation 20 meters, and within 6 days, as you see here from 0 to 6, the water table linearly decreases from elevation 20 to elevation 14. And we will go and investigate what is the effect of this change, drawdown, on the factor of safety. Okay. This one, since we are going for transient analysis in the project setting, groundwater, we are going for method steady state finite element, and we are selecting the advanced option, which is in this case transient groundwater analysis. In the transient tab, we have 5 stages defined here, and we are looking at the effects of this change, drawdown, at days 2, 4, 6, 10, and 50. In the steady state groundwater analysis, as you see here, the water table stands at elevation 20. I have added these 3 discharge sections as well so that you can see what is the flow through the body of this embankment. And in the transient stage, we have this transient boundary condition indicated in red here. And you can define this transient boundary condition from this icon here. So transient boundary condition. The one that we are using here is the gradual drawdown. And if I edit, you can see that, okay, this type of boundary condition, we have all the list here. It's a total head with time. This is the time table for changing of total head for this example. And we have the seepage face condition selected as well. The seepage face condition selected means that if this portion of the boundary is resurfacing coming out of the water, it will get seepage face condition. So let's look at the results. I will explain it on the results even better. Okay, so the results that we are looking at, we have the initial state and all the transient stages listed here. The initial state, you can see that the factor of safety is 2.2, which is pretty safe. And you can see that the flow, the discharge, is 1.32, 1.32, 1.32. It's constant for all these three discharge sections that I have there. This was steady state condition, inflow and outflow in the system, they're going to be the same. Now, when we start to gradually bring the total head down in the upstream, you can see that, okay, the factor of safety dropped down to 1.8, and you can see the flows are changing, and actually we have some flow going from the embankment towards upstream. Day number 4, the factor of safety drops more. You have more flow going from the body of embankment towards the upstream. And day number 6 is the most critical case that we have here. The factor of safety is actually dropping below 1, so it is not safe anymore. And if I activate the flow vectors, you can see that, okay, the flow happens from the body of the embankment towards upstream and downstream. And if I zoom in here, you can see these bunch of nodes here that actually flow is coming out of them. These are the effect of that seepage face condition that I selected when I was assigning that transient boundary condition. So what happens here, let me turn these off. You can see that, okay, because of this dome that you have here, this is the water surface. You have high pore pressure values inside the body of the embankment. And because of that, let me activate the pore water pressure underneath the slope. You can see that these values are rather high and they are not in equilibrium with the upstream and downstream. You have lower effective stress, lower shear stress, and you are getting lower factor of safety in this case. Okay. Now let's go continue with the examples. This is the last example that I will introduce. In this one, we are using the piezometric data grid to define the pore water pressure in the field. The example is on tailing dams, and we are considering the construction of this new embankment, the yellow material, on top of the tailing materials. So we are looking at construction of new embankment in a tailing dam. The way to handle these kind of problems, we have to look at hydromechanical coupling, and we have to look for an alternative formulation that can handle this kind of interaction, that can handle consolidation formulation, consolidation problem. And we are looking at, like, for example, coupled bioformulation, which we have it in our program RS2. This is RS2 model of this example. You can see the mesh, everything, all the boundary condition. It actually looks like a slide, but this is our finite element program. In the project setting, I will show you that we are actually doing a consolidation analysis using our coupled bioformulation. In the stages, we have initial stage and another stage that we have time and drain, which means that we are doing consolidation analysis. In stage 1, we don't have this embankment. In stage 2, the embankment will be built. And stage 2 is going to be the one that we are actually running the consolidation analysis, and we are calculating the pore water pressure and all that will be built because of construction of this new yellow embankment material. And let me just show you properties of the material here. When you are going for consolidation analysis, you have to account for the behavior of material, not only strength of the material. The material that I'm using for the tailing here, I'm using Rocscience considered model, which is one of those advanced material models that can capture static liquefaction, for example. And based on this, I can do my consolidation analysis. And after that, in the interpret, when I look at the results, this is my initial state for water pressure distribution. And after construction of that embankment, we have another distribution for water pressure in the field. Then I can export all of these, export values at the node. And then all these values, I can import them as grid to slide and run my slope stability analysis. So that's what I actually did in this example. Okay, so this new embankment coming in, we are doing compiled analysis, consolidation, and we are using one of those advanced material model Rocscience. What you're looking at here again, you have the initial pore water pressure and excess pore water pressure calculated in RS2 for one of the cases that I have analyzed, where you have the use of application of consolidation formulation and advanced material model. Let me go back to my examples. So just to emphasize what we are looking at, I have all the contours of pore water pressure distribution in the domain here. This is initial state. If I was going for elastic analysis for my tailing materials, I would get excess pore water pressure of 170 kPa, for example. This is the case that I'm actually building the embankment in 20 days. If I was going for a loose sand using north sand material and I built the embankment in 7 days, I would get this excess pore water pressure distribution in the domain, which is like 600 kPa maximum value. Comparing to the elastic one was 170. This one is significantly higher. If I'm building the embankment a little bit slower, so we have more time for the excess pore water pressure to dissipate, we can see that, okay, the maximum excess pore water pressure is 570. If I have more time, 20 days, for example, it's 520. And if I'm looking at a slower rate of construction, I have 490 excess pore water pressure in the domain. Now, let's go to slide modeler for this. The way that we handle this in a slide, the first scenario is the one that we actually have initial state. I can actually, the dots, that the symbols that we were looking at, and I deactivated them, these are the grid points. So we define the pore water pressure for all these, and then the engine, the slope stability engine, is going to calculate the factor of safety. It can evaluate the pore water pressure at any point by interpolating between these points. The first scenario is already defined here, initial state condition. For the second one, where we have this embankment constructed, I will define the scenario completely for you. So I can go to groundwater. I will go to grid, pore water pressure, and now you can define the grid. So the grid is defined XY coordinate of the point and the pore water pressure. The output that I got from RS2, for example, is in this Excel file. So it's a loose material for 20 days period for the construction of the embankment. This is the excess pore water pressure that we saw for it, and this is the new pore water pressure distribution in the domain. These are the values. These are the output that I got from RS2. So I will select all these values, copy them, bring them in a slide, paste, and all those values are now here. Press OK and OK. So these are all the grid points that we have to establish that field of pore water pressure in this domain. Just to take a look at it, you can go to property viewer. Let me actually deactivate these symbols. This is the pore water pressure looking when we have the construction of this embankment layer. This one, let me go back to this one, close that one. The first scenario, let me deactivate the grids again. Look at this one as well. This was the original configuration for pore water pressure. And this one, let's look at them side by side. Okay, like zoom, you can see that, okay, the one that we have the construction of this new layer, we have higher pore water pressure in this area. Okay. Now let's run this example. The first one, we already have the results for it calculated. The second one, I just defined it. We can look at the results for it. We can already see that the factor of safety is below 1, but we will see the comparison between the initial state and the state that we have this embankment constructed. Okay, results are ready. Let's take a look. Just to make it more clear, I'm just going to go to groundwater tab, deactivate these, grid points. I will tile the view like the zoom, and now you can see the factor of safety for the case that you have the new embankment constructed. I'm just going to show you the pore water pressure. Underneath the slip surface. So this is 670. In this case, I'm going to try to show it as well. This is 51. So significantly, we have excess pore water pressure in this case. And because of that, you are losing that factor of safety of 2, and you are actually going towards failure. Now, this was a schematic, just example that I showed you. You can actually investigate more features here. Let me close all these. You can investigate the rate that you are actually constructing this embankment. This one that has the details. Let's look at this example. So this has different scenarios here where you are building the embankment in 7 days, 10 days, 20 days, 30 days, and if you are assuming that the material is actually elastic. So looking at the results here, I'm actually opening the modeler. Let's look at the results in the interpret. All the scenarios are being opened one by one. Okay, let me extend it here so that we can see what we are looking at. So the first one, if the failure was going through the embankment, it was close to 2. The second one, if you are building the embankment in 7 days, your factor of D is very low, is 0.5. If you have more time for the dissipation of excess pore water pressure, you have 0.6, 10 days here. 20 days is the case that we actually solve. Is let's look at the Spencer method actually, or GLE method, synchronize all the methods. So we have 0.9, 30 days, it is actually above 1. And just in case we did not use the Norsen model in our finite element analysis, the consolidation analysis, and we use elastoplastic more Coulomb, for example, the evaluation of excess pore water pressure would not be that accurate. And in this case, for example, comparing to the 20 days that we had the Norsen was 0.9. Elastic one is giving you 1.7. So if you do all your calculation correctly, you can get the right factor of safety out of all these set of tools that we have. Okay, let's go back to the presentation. To sum it up, as for seepage and slope stability analysis in the slide 2, we have various options to incorporate the pore water pressure and also the water load in our slope stability analysis. We have water surface, piezometric data, RU coefficient, finite element seepage analysis, all these methods built in slide 2. On top of that, this finite element seepage analysis engine that we have included in a slide can do steady state and transient analysis, and we have tons of options for them. And I'm just going to wrap up this presentation by inviting you guys to part 3 webinar. It's going to be on May 22nd, 27. It's on support and probabilistic analysis. And thank you very much. Now I'm going to go through the questions that we have. I'll try to answer as much as I can. Question number 1, it says that in the 17-channel model you showed, why you use the fully saturated tension crack zone, would you get the same result if the unit weight of the material below the water level are as saturated? Why did I fill the gap fully with the water? That was actually the scenario that actually happened. So the gap opened all the way up to end of the sheet pile, and that's what I actually assigned there. So, and the water level was at the elevation 9.5 where the flood water was. If the unit weight of the water was different, all these materials that I used there, most of them, they were like a cohesive material. So in a sense, that unit weight is not going to change it much, but all those layers that we have there, there was a pink weak layer there, and everything was going through that weak layer. So if you have the loads affecting the drive force, the load that are coming from the weight is going to affecting that, yes, in that sense, it can affect the factor of safety. But none of the loads there would affect the effective stress and would affect the shear strength of the slip surface. Question number 2, could you please at the end stress the advantage of Slide over other limit equilibrium software, especially when it comes to the analysis of reinforced element like anchors and soil nails? Well, Slide is one of our most user-friendly softwares in Rocscience and also everywhere else. If you use Slide compared to other products that are available in the market, you will find out that Slide is way more user-friendly. On top of that, Slide is packed with features. We have tons of support elements, and some of these support elements are actually standardized by the support manufacturer. So all of these are included there. We have different support companies joining us, and we have the library of support that they manufacture. We have them all in the library of support that we have. On top of that, we have the combination of Slide and RSPile. RSPile is another program that we have for finite element analysis of piles. And combination of these two, you can analyze the piles very accurately. You can have the forces of the pile calculated correctly and used in the calculations of factor of safety in a Slide. The Slide and RSPile, they will communicate with each other, and with an iterative communication that they have between each other, you can calculate the correct pile force, use it in your slope stability analysis. What is the difference between carrying out the seepage analysis in a Slide and RS2? Slide and RS2, they use the same seepage analysis engine. So as finite element wise goes, they both use the same engine, and every boundary condition and all that, these are the same. The only thing is that in RS2, we have the consolidation formulation. So the loading that you're applying to the solid, it can affect the pore water pressure in the domain. In a Slide, this coupling is one way because this is limit equilibrium. It's not the weakness of a Slide. This is limit equilibrium method. You have slope stability analysis, which is using the pore water pressure. If you would like the hydromechanical coupling, you will have to use the consolidation formulation that we have in RS2. Other than that, the steady state and transient analysis, they use exactly the same code and the same engine. Why did the last example we did it in a Slide and not RS2? Because this presentation is actually in Slide 2, and I just wanted to show you that all these cool tools that we have, we can mix and match between them. If you have a specific problem you want to address, you can throw any of these tools at it and solve it with different approaches, different tools, different formulations. In many cases, if you're solving the same problem with different tools, different formulation, and you're ending up with the same results, you can be sure that, okay, the analysis that I did is okay. If you are coming to results that are different between the tools, different between the formulation, then you will have to investigate it a little bit further to see which one of these scenarios is giving you the better answer. Why are you doing the slope stability in a Slide, not RS2? Yeah, it was Slide analysis. Actually, RS2 was also giving me failure for this case. Let me close this. The way that things fail in RS2, if I open it in interpret, if simulation fails to converge, means that it is not stable. When you open the simulation in the interpret, you will see one of these warning messages. It says that the number of iterations exceeds the maximum number of allowable, meaning that the convergence may not have been established or there is some problem there. In this scenario that we saw, all the cases that I solved, actually, you saw that the factor of safety was below 1, so it was unstable. RS2 is also confirming that scenario. So both of them are giving you instability. Is it possible to investigate liquefaction in RS2? I just actually did that. So those areas that you saw, those high pore water pressure, if you look at the RU values for them, let me show you actually. It's not actually liquefaction, but RU is going to be the ratio of vertical stress over pore water pressure. Let me show you RU values. and I don't actually have that in this example. Let me show you effective mean stress and query data point. You can see that these effective stress are a lot lower values than it's supposed to be originally. Let me actually, I can calculate that. Data, I can define user data. My user data could be equation. Let's look at RU, which is going to be my pore water pressure divided by my effective stress. Where is my effective stress? Effective stress YY E SYY. Let me see if I can display it quickly for you guys and display contour. Let me go to contour option, go between 0 and 1.1. You can see that these areas actually, let's look at this one in another example. Then I can show you actually, yes. So in these areas, you can see that RU is rather high values and you have the liquefaction in these areas. Okay. I have no more question listed for me. I'm actually, my colleagues are sending me the question on my phone so that I can read them and answer them. Thank you very much for joining us. If you have any more questions, you can email us. We will look at them and try to answer as many as we can. And we can wait to for you guys to join us in the next webinar on May 27th. Thank you. Bye for now.